So last time we left off discussing light scattering. So this is related to zeta potential. So we need to understand light scattering first, then we can understand how we can use light scattering to measure zeta potential, which is the closest thing that we can measure to the surface charge, or sorry, surface potential, right? If we understand surface potential, we can start to get an idea of whether a colloid is stable or not, as you saw in the problem that you had to do in homework. If you have an understanding what the surface potential, we can start to understand what the energy barrier is for in DLBO theory, and then assess whether the system is stable or unstable. Okay, so in terms of designing colloidal systems, we want to design them such that they have a surface potential that either allows them to be colloidally stable, if that's what we want, or if we're trying to separate something, for example, we want to reduce their surface charge somehow and be able to measure that. Okay, so last time, again, we have this picture here that illustrates the idea of where our surface charge and slipping plane is. The slipping plane is the amount, what would move along with the particle if you were to apply an electric field. Because this is dragging a bunch of ions, this quantifies sort of the plane at which this happens. So when we measure particle size, for example, we'll be measuring that as our particle size. For example, if we're trying to understand the mobility of the particle. And the surface charge will be the charge at the surface of the slipping plane, which is known as the zeta potential. So we talked about this idea, the setup last time for light scattering, which is pretty straightforward. You shine a laser on a colloid. The colloidal particles are undergoing Brownian motion, and you get some signal that comes out. And the signal at first looks like a bunch of stuff that is pretty difficult to understand. So again, here we're seeing that I'm showing what the intensity versus time of something like this would look like. So what does this mean? So every time a particle passes in front of the laser, you'll have a dip in the intensity. Or sorry, it should actually be an increase in intensity is when that happens. Sorry about that. So you have scattering. You have scattering, which means that the light gets deflected over to the detector when you have particles that are there. So depending on the amount of particles, how fast they're moving, at any given time, you will have a different amount of particles that are there because they're undergoing Brownian motion, which is quite fast. So that's just an increase in intensity due to particles passing the laser. Okay, so what we would notice if we were to have different particle sizes, so let's say that these are, let's call these some nominally small particles. For big particles, you would see a difference that would be pretty apparent. While it would still look quite noisy because what we are measuring is thermal fluctuation, which is in most measurements, that's just noise. What we would see though is for bigger particles, if we were to plot this on the same time scale, we would see that the amplitude or the frequency of this really would go down. Okay. So based on that, we can correlate essentially all the features that we see in there The math behind this is complicated, but it is a mathematical technique that's called autocorrelation. So typically what you would do is apply this, you would extract something called the correlation coefficient. And I'm going to skip the math here because it's not worth our time to go through all these details because it would take a whole class just to go through that. And if you measured time, so typically this would be plotted on a logarithmic plot. So let's say this time is in microseconds, and so that would be 0.1, 1, 10, 100. You would get some curve that looks like this. So if we had, let's say this is for our small particles, and for our big particles, we would have some time, correlated time that was longer. So this time is basically the time at which these particles are moving this sort of constant distance across this laser beam. So that's related to the velocity of the particles, and we know that that smaller particles are moving faster. So this is a direct way to get diffusion coefficient. So I'm just going to, you should understand that concept. So you can do some math, let's say simply, and you can get the diffusion coefficient. Remembering that the diffusion coefficient is related to the net mean displacement, or sorry, mean squared displacement of a particle and its time, the time at which it takes to do that diffusion coefficient. So the big message here, if you want to summarize what light scattering is doing, is light scattering, specifically dynamic light scattering, so just to be clear, dynamic light scattering is measuring this with time. You could also just shine light, like one pulse of light, and measure whatever signal you get out. That would be static light scattering. And for this type of system, is not particularly useful. So that's useful for things like X-ray scattering to determine the structures of materials, for instance. So dynamic light scattering is basically measuring Brownian motion within the system. And from that, you can get diffusion coefficient. And from more assumptions, by making more assumptions, we can relate through, so for example, the Stokes-Einstein equation, we can then relate diffusion coefficient to the size of the particle, right? And if we know something about the particle, like what it's made out of, we can understand like the mass of the particle and things like that. So we can get some information. But remember, the size that we'll be measuring here is the height the hydrodynamic radius. So from diffusion coefficient, we can get size through Stokes-Einstein equation. But remember that this size is the hydrodynamic, let's say diameter, the hydrodynamic diameter, which again is the particle plus that slipping plane distance, because that's what's moving through the system. Okay, so depending on the size of the particle, the slipping plane distance might be very large. So for instance, in the case of, we've measured Debye lengths. If we remember, Debye length is going to be a bit further out. So say, just illustrate, it's going to be some distance bigger than the slipping plane. And we know that depending on the salt concentration, this can be something like a nanometer to 10 nanometers. And the distance out to the slipping plane is typically within a few ionic diameters, sort of like what's shown in this picture. So, you know, considering an ion is something typically like on the order of an angstrom or so in diameter, maybe 2. It's going to be a pretty short distance to the zeta potential. So it's going to be quite similar to the particle diameter within typically within less than a nanometer, but it's going to give you a slight overestimate of the particle size. So I think that's again the key message. Slight overestimate of size. Okay, so that's dynamic light scattering. It measures Brownian motion and can give you an idea of size. Then the question then is, how can we measure zeta potential? So again, we have an idea now of how, if we have a particle and it has a charge, we can, and we're able to measure how fast it moves on an electric field. We can directly apply our physics 2 principles, right? If we know the charge, we know the mass, we know the physics to be able to understand this. So again, I am going to skip a lot of the quantitative aspect of this, but suppose you have a particle and you know, it's undergoing Brownian motion, but it's not moving in any particular direction. So suppose you shine a laser beam on it. So you have some light here that's coming in. So this is a light wave. It has a frequency f1, right? Frequency is the distance between the peaks in this wave. So if say it's not moving on average, it will scatter some light. Some of this light will be scattered. And this light will have the same frequency as the incoming light. F1 on average. We know that they're undergoing Brownian motion, so they have some velocity. So, but all the velocities will be in random directions. So all of them will average out. So the average frequency of the light coming back in terms of, or being scattered will be the same because all of the different frequencies would cancel out. So what would happen if this is moving on average, though, is the Doppler effect would take place. So you probably learned the Doppler effect maybe in physics 1. So for example, the Doppler effect is how we understand how far away stars are moving away from us. We know, like, for example, the colors of stars have to do with the spectral lines of hydrogen, for example. And we know if something's moving away from it, that stretches out the wavelength. And we can understand how fast it's moving away. Or if it's moving towards us, it'll shrink the wavelength. So if it's moving away, and here I'll draw an arrow to indicate it's coming in this direction. So we have this wave coming in, that has a frequency of 1. The scattered light, if it's moving in this same direction as the light, the frequency will actually get longer. So again, this is called the Doppler effect, which is well known in physics. And I imagine that you should have learned that in physics 2, maybe physics 1, sometime when you learned about waves. So this is a property of waves. Okay. So so again, this is if it has some velocity on average. So the velocity can be induced. There's a couple ways to do it, but the most common way to do this is by applying an electric field. So so by applying electric field, we can vary, for example, the strength of the electric field. Usually what they do is they put it in an oscillating electric field and vary the intensity of that electric field. And we can then measure this difference. Okay, not again. Come on. There we go. So again, when you put particles in an electric field and you watch them move, this is called electrophoresis. And you can measure the electrophoretic mobility. So mobility is directly proportional to the velocity of a particle, which you can measure from Doppler effect. And mobility is also directly related to the diffusion coefficient. Okay, so any questions about that? Let's make sure my chat window is open. No. Okay. So just to be clear, so diffusion coefficient mobility relationship is what is it? Would be the diffusion coefficient equals mu, which is the mobility, kt over q. And let's call this mu q, where this is the electrophoretic mobility. Okay, so that's the basis for this. So we can measure, from that, we can measure diffusivity. We also can obtain the surface potential from this. So there's a couple different ways, because we can measure diffusivity 2 different ways here. So since we measure from dynamic light scattering, we already got diffusion coefficient. This can also give us diffusion coefficient again, or mobility. So by comparing, so here, let me make this clear. From dynamic light scattering, we get diffusion coefficient. And from doing this electrophoretic mobility, we can electrophoretic mobility measurement, or let's say basically that's doing DLS with electric field. From the electric field measurement, we can get mu q. So by combining these, we get the charge, which in this case will be our zeta potential. Okay, so just to be clear, so Q we're using as generic charge, not the fundamental charge. Been using E for that. Okay, so Q here is what the charge of whatever you're measuring in this case, because this is a particle with a this will be, let me back up. This is not exactly zeta potential. This is the surface charge of the particle. Surface charge, sorry about that, at slipping plane, which is directly related to zeta potential. Okay, so that's the relationships that we need to understand. So again, the takeaway here should be that we can understand the motion of particles both by measuring Brownian motion directly, then by applying electric fields to perturb the system and induce a velocity, we can obtain more information. And by applying some relationships from physics, we can get information about how big the particle is by understanding its diffusion coefficient. If we know the viscosity of the solution and the temperature, we can apply Stokes-Einstein equation to do that. If we apply electric field, we can apply basic physics 2 equations to understand the surface, the charge, and thereby the potential at the surface. Okay, so let's stop there. I want to move on to a different subject. Because we want to start getting into some more practical things. So let me pull up my notes. This will probably disappear for a second. Okay, so this is covered somewhat in the very later part of the textbook. So you can follow this along. This is actually going to be either at the end of section 2 or the beginning of section 3 of the textbook. And we're going to talk now about micelles. So we talked about surfactants briefly before, if you remember. Okay, let me get this back up. Okay. Okay, so surfactants, we remember, are molecules that have a strong polar component and a non-polar component. So if we have some liquid film, say of water, and we know that if we have these surfactants, they would have a polar head that would remain in the water and a non-polar tail that would stick out. So surfactants preferentially move to the interface. Right? This is an effort to minimize the free energy of the system because it's unfavorable for that nonpolar head to be inside of the liquid water. So it moves to the outside of the polar environment to minimize the energy of the system. So we can think about this from a thermodynamic point of view. So surfactants can take a couple different structures. So there's a simple thing that we drew before where there's a polar head, non-polar tail, but it also could be dimeric, meaning there's multiple heads, or two heads in this case, or polymeric. So they're polymeric surfactants. So in that case, you'd have a bunch of heads, for example, that are linked together with tails. And that would extend for some distance to give it a high molecular weight. They can also take the form of some kind of copolymer. So for example, it could be a diblock copolymer or even triblock copolymer. So we have a whole class on polymers here, so I'm not going to go into a lot of detail about this, but the idea is that there can be a bunch of this part that is, say, hydrophilic or hydrophobic, and some part that's hydrophilic. So this could actually lead to some really interesting phenomena because this is a molecule or a polymer that has two parts that don't like each other from an energetic standpoint. So when you assemble these polymers, say like into a film, they'll form really interesting structures to avoid the parts that don't like each other touching. So this ends up making this a very unique avenue for designing certain types of materials. So actually, Eric Cochran in our department does a lot of research in this area, if you're interested in learning more. So we can think about this idea here. So up at the top here, we can say that these surfactants adsorb to the interface. So typically, in engineering or chemical engineering, we think of adsorption as some process that's happening between to a solid. So we talk about gas, for example, absorbing to a solid. In reactions, we talk about catalysis, right? Oftentimes that is a gas phase reaction where we have molecules in the gas phase that are absorbing to the solid. In this case, we have what's essentially something that's considered to be a solute that's in a liquid, but it's the same process. So the molecules preferentially go there. We would say that's absorption. So there's some things that happen that are interesting. So we can measure the surface energy of this. So remember, we have gamma surface energy, or in this case, because it's a liquid, we'll call it surface tension. And if we were to look at this as the concentration increases, we would see that as the concentration increases, for some time, the concentration would go down because the adsorption of these molecules breaks up the intermolecular forces. particularly the strong ones, such as hydrogen bonding. Since the water molecules can't be next to each other because we have this adsorbed layer that's getting in the way of the water molecules, the surface energy goes down, right? Think back to how we were talking about surface energy. It has to do with the cohesion of this material. By introducing these, we will break up this surface, and that would break the cohesive forces within this, and result in lower surface tension. So this is something that you experience in everyday life, right? You know that if you take a droplet of water, which is high surface tension, and you add some surfactant, say for example soap, to it, it will break the surface tension, and that droplet will spread out, right? So we see this in everyday life. So one thing that you would notice, if you at some point, if you continue to increase the concentration, this won't happen indefinitely, because the surface does not have infinite number of places that it can go. So in this region here, we can say, so here the absorption is happening, and in this region, the surface is saturated. And in that case, the additional surfactant molecules are dissolved in solution. Okay, we just talked about how the fact that it's unfavorable for these organic or non-polar hydrogroups groups to be inside water or a polar solvent, right? So in that case, like what would the most energetically favorable thing to happen? If it's forced to go inside the solution, what will it do? So to minimize free energy, surfactant molecules form micelles. Once, or I would say after the surface is fully covered. So what happens is, again, let's draw this as a sort of container of water. So the surface is full. Is occupied. So adding additional micelles, this organic or nonpolar head or tail group is unfavorable. So what will happen is that these will organize into micelles. Okay, so going back to this diagram up here, so this point at which we see this surface tension stop decreasing in a linear way, we call this the CMC, or critical micelle concentration. Okay, so we can directly do a measurement because we can measure surface tension or surface energy of a liquid, specifically of water. It's quite easy because we can just look at what the contact angle is, and that's directly related to the surface tension, if you remember our analysis of liquid drops that are sitting on a surface. So we can basically just look at a drop of water as we are adding a different amount or concentration of surfactants, and we can identify the surface tension, and we can understand how the surface tension varies with the concentration. So it's quite straightforward to measure the critical micelle concentration of a system. So it turns out that this has a bunch of different the presence of micelles in solution have a bunch of different impacts on solution properties. So we can look at some generic solution properties or some common solution properties that are important versus concentration of surfactant. So again, we have some concentration here, which is going to be the critical micelle concentration. So we know that the surface tension will go down. But there's some other aspects of this that will change too. For example, detergency of a system, which is the ability of a surfactant to pick up other molecules, will also change. So for example, if you're trying to formulate a system such as like laundry detergent, for example, you want to avoid it being at the critical micelle concentration. You want your system to be below that because every additional molecule of detergent you add past the critical micelle concentration is not giving you any more detergency, which is the ability to function as a detergent. So that's why if you are doing your laundry, adding a cupful of laundry detergent is not going to help you any more than adding a spoonful because there simply isn't an additional ability for more of this to pick up more dirt. So that also comes into play with when we're designing detergents or a system to, for example, wash clothes or wash dishes or clean anything. We want to design this detergent system such that we can get as high of a concentration of these surfactants without it forming micelles. So avoiding the formation of micelles in the case of cleaning things is favorable. Okay, so in other cases we want to form micelles, and we'll get into that later. So other things are interesting. So for example, the osmotic pressure, we know that for these surfactants, at least the way that we're drawing them, are oftentimes ions. We know that these polar heads tend to be ionic, things like cationic or anionic groups. So we know that the osmotic pressure is typically a function of ions. But what happens when these are tied up into micelles, the osmotic pressure also flattens out. And that's because the ions when they aggregate into these micelles, are no longer accessible anymore. So effectively, it decreases the concentration of things that are dissolved in there, even though, yeah. So that's another phenomenon that happens. So there's a number of properties that change. Other things like it can dramatically affect the viscosity of the solution. So that's why certain food products like mayonnaise, for example, what happens in mayonnaise is you emulsify oil and water together, essentially, and you end up with a material that's much more viscous than either of the starting materials by adding a very small amount of surfactant. So mayonnaise is typically what's traditionally added is egg yolk, which has a couple different types of surfactants, such as lecithins. So the viscosity can dramatically increase. In some cases, turn it into something like mayonnaise, which would not be described as a liquid, but more of a complex fluid because it has some properties of a solid as well. Okay, so that's a very non-Newtonian fluid in that case. Okay, any questions about this? No. We'll check chat. Okay, we got a few minutes left. And there it goes again. Okay. So the structure of micelles we've sort of talked about. So under low concentrations, we have this sort of picture I showed you. In 2 dimensions, it would look like this. Where the length of this, or the diameter of this, would be about 2 times the length of a surfactant. So in 2 dimensions, that would be a cross-section of it. In reality, it'd be a sphere that looks like this, where each of these would occupy a cone worth of volume. At high concentrations, though, this becomes much more. So I alluded to this before. There are let's see. We can, for the case of ionic surfactants, meaning that the head group is ionic, we can create a phase diagram for these. So we learn about. So if we were to plot concentration versus temperature of micelles, what we would find is at high concentration at low temperature, at some point, these would just form hydrated crystals, meaning the surfactant molecules would just sit in solution, right? Or they would clump up, they'd form some kind of crystals that have water associated with them, but they'd be solid. At very low concentration, there will be monomers, meaning unassociated micelles. And at some boundary here, we'll have micelles, where this dashed line here would be the CMC curve. If you were to draw the CMC versus temperature, that would be that right there. So again, you know, this has some similarities to something like the triple point, right? So for like, you've seen these phase diagrams, you have a place where all these phases meet at some temperature. Instead of pressure, we have concentration. Okay, so other things that we should know. Again, right now I'm just sort of spitting facts at you about micelles. How much time do we have? Probably close to the end of class. Oh, we got 4 minutes. Okay, so so this is the case for ionic surfactants. For non-ionic surfactants, if you increase temperature, decreases solubility. So regardless of what type of surfactant, these things are defined, these micelles are oftentimes defined by what we call a cloud point. So this is the temperature at which aggregates start to appear. So you'll have a solution, and you either raise or lower the temperature depending on whether it is a ionic or non-ionic surfactant, and you will start to see it go from a solution to something that's cloudy, meaning that you're forming aggregates of surfactant molecules. So this is oftentimes a way that this is characterized. You can do this in a very quantitative way by changing the temperature really slowly and measuring light scattering of a solution, because rather than looking at by eye, there will be a big jump in the light scattering when you have particles that are big enough to make something look cloudy. When something looks cloudy, that has a different type of scattering happen. So the light scattering that we talked about is something called Rayleigh scattering that happens for small particles that are smaller than the wavelength of light. And it doesn't look like anything in solution. For large particles that are on the order of the wavelength of light or bigger, there's a different process called ME scattering, M-I-E, scattering that occurs, and that causes things to look cloudy. So if you ever see a solution that's cloudy, that means it has that means ME scattering is taking place, and it has particles in there that are on the order of the wavelength of light or larger. So typical wavelengths of light for blue, for example, will be 400 nanometers in size. So that means that you would expect any type of cloudy solution to have particles that are 400 nanometers or larger. That's as a rule of thumb. Usually you'll say wavelength over 2 is what, so at least 200 nanometers. So anything that has suspended particles of less than about 200 nanometers would look optically transparent to us. It might have a color, but it would be transparent. Okay, what else? So we're right at 159. We're going to continue upon this a little bit, and we'll talk about some more complicated micellar structures and what they're used for. So we'll continue upon that on Friday, not Wednesday. Oh, sorry, Wednesday, not Friday. So this should be Wednesday. Okay. So I will see you all on Wednesday.